It seems likely that a small inflatable boat filled with air will stay afloat on water. But how can a massive cargo ship extending over 3 football fields in length and weighing more than 24 Eiffel Towers stay afloat? In this animation, we will study fluid dynamics and Archimedes' principle to understand how these colossal steel ships can float on water. Let's first review the nearly incompressible nature of water. If we fill this beaker with water, the water pressure, or hydrostatic pressure, will build on the bottom of the beaker and push out in all directions as the arrows and pressure gauge indicate. Most importantly, they even push up, holding up the water above. For example, if we look at a specific point halfway on this beaker, there is both water above and below this point. Now, the water above this point is pushing down on the water below, hence the high pressure that the gauge is indicating. This higher pressure pushes out in all directions and even back up on the water above it, keeping it in place. Keep in mind that the water pressure at any height is dependent on how much water is above it. Now let's explore a more practical demonstration to better grasp how steel ships float. This is a cut-through of an in-ground pool. This single cubic foot of water weighs just over 62 pounds or 28 kilograms. It pushes down on the water below it, forming hydrostatic pressure. The hydrostatic pressure accumulates the deeper you go. 5 feet down, the pressure is 312 pounds per square foot, pushing down. Now, what's holding up the 312 pounds of water? Where does all that hydrostatic pressure come from? Well, the water at the bottom of the pool builds in hydrostatic pressure the more water that is above it. For example, any water above this green line contributes to hydrostatic pressure that is pushing up against the 312 pounds of water, as the long red arrow indicates. Now that we have seen how water is able to hold itself up, how does it hold up ships made of steel? Well, let's go one step further and first swap out 1 cubic foot of water with a crate that has the same volume and weight as water. The crate sits in water pushing down with 62.4 pounds of pressure, and the water just below it pushes up with 62.4 pounds of pressure, just as if the crate was water. But what if we use a crate that takes up the volume of 2 cubic feet of water, but only weighs as much as 1 cubic foot of water? Well, this is where things get interesting. The crate is displacing more weight in water than the amount it weighs itself. The water at this depth is pushing up with 124.8 pounds, but the crate only weighs 62.4. Because the hydrostatic pressure under the crate at 2 feet of depth is greater than the weight of the crate itself, the hydrostatic pressure will push the crate up. But as the crate rises, there is less hydrostatic pressure below it, and the two forces will eventually balance themselves out. Now, what if we add weight to the crate? Let's add a 50-pound kettlebell and see what happens. The crate now weighs 112 pounds and is displacing only 62 pounds of water, so the buoyant force is only 62 pounds. This will cause the crate to sink, displacing more water. It will continue to sink until it displaces 112 pounds of water. As long as the floating object can displace an amount of water equal to its own weight, it will stay afloat. This is a perfect demonstration of Archimedes' principle, which states a body immersed in a fluid, like our crate being in water, will experience an upthrust equal to the weight of the fluid displaced. Now, returning to the question of how massive steel ships float, the key lies in displacing 1 ton of water for every ton they weigh. And with a ship's massive width and length, it's able to displace an immense amount of water. The ship's position in the water will simply adjust based on its weight, displacing more water to maintain an equilibrium. Thanks for watching this animation, and I'll see you on the next one.